Medical AI has gotten really good at reading X-rays. But here's the catch. Almost all of it was built for adults. When you feed a child's X-ray into these models, performance drops off a cliff. Why? Because children are not small adults. And today's paper, PedCLIP, fixes that. So why do adult trained models fail on kids? Three reasons. First, anatomy. A child's lungs are smaller, their rib cage is still developing, bone proportions look completely different. Second, pediatric X-rays use low radiation doses that changes image texture and contrast in subtle but meaningful ways. Third, and this one is sneaky, almost every major vision language model out there was trained almost entirely on chest X-rays from a single adult dataset called MICCAI. So the model basically only knows one body part. Show it a wrist or a knee, it's lost. PedCLIP addresses all three, but the most architecturally interesting fix is for the third problem. So they collect 400,000 pediatric X-rays spanning 23 anatomical regions: chest, wrist, knee, hip, and so on. Great. Now just train one big model on all of it, right? Wrong. And here's the intuition for why. When you train a single neural network on widely different body parts, the features start fighting each other. A wrist looks nothing like a chest. The model's internal representations get pulled in conflicting directions. What's useful for understanding a fracture in a wrist actually interferes with what's useful for detecting a heart condition. This is called feature interference, or more formally, negative transfer from multitask learning. The minority body parts just get drowned out. The solution PedCLIP uses is called Mixture of Body Part Experts, or MoBE. Instead of one shared MLP inside each transformer layer, they have multiple expert MLPs, one specialized per body part, as you can see here. So think of it like a panel of specialists sitting together. When an X-ray comes in, a gating network looks at the image and says, this is a wrist, and routes most of the computation through the wrist expert with small contributions from others. The gate is soft, not hard. So shared findings like general bone density or soft tissue swelling can still bleed across experts, but each anatomical region gets its own dedicated representation pathway. No more drowning out, no more feature interference. And crucially, these experts are placed in the later transformer layers where the model is already working with higher level semantic features, not raw patches. This architecture, combined with a carefully curated dataset where an LLM extracts body part specific text from radiology reports, gives you a model that genuinely understands pediatric imaging across anatomy, not just chest, everything. It outperforms every prior VLM in both zero-shot and fine-tuned settings, including rare conditions like pediatric inflammatory arthritis, which almost no prior model even attempts.